Over 45 years of engineering work, we have seen firsthand how technology has evolved. We have seen what was invented and what got implemented. We have seen what has staying power and what are passing fads. Our view of Industry 4.0 came to a simple but profound conclusion. Industry 4.0 means our world has become two worlds, not one. From the first telex to the first Excel spreadsheet, the digital world over the last 50 years has been catching up to the real one. Today, with massive computing power, the digital world has truly come to life. It has its own characteristics. It is not real, clearly, but it is also hyper-real at the same time. Our view of Industry 4.0 is simply that it is important to recognize, accept, and live in two worlds at the same time. You may think this is far-fetched. It isn't. We are already doing it. Checking your phone while crossing the road? Guilty. iPads in front of kids while they eat dinner? Done. Here are some examples in the context of our industry: digital workspace and physical workshop. The digital workspace is your computer screen. On this particular screen, you see a 3D model of a turbine engine. You move it, rotate, zoom in and out with a swipe of your fingers. You look over and under the engine, and information pops out automatically. In the real world, an engine is an ultra-heavy object. Every simple movement is a Herculean task. This can only be done in a large workshop with enough space and height clearance. In this picture, the lifting of the rotor alone requires heavy-duty equipment. You need a 100-ton crane and weight-certified lifting belts. Digital report and physical repair. Anything that is not handwritten or drawn on a piece of paper is in theory a digital report. By this definition, we have been using digital printouts, graphs, and Excel spreadsheets for a long time. What's new is that with augmented reality, or AR, we can take 2D reports and superimpose the information onto real-world objects. Here we read the status of a row of motos. Data is superimposed on each moto. With no experience, anyone will spot that moto number 2 has an error. Let's say that the error turns out to be a damaged motor that needs to be repaired. So we shift from this digital report into the physical repair. Here is one of our skilled rewinders, 30 years of experience. He has honed his craft over hundreds if not thousands of motos. He is rewinding the stator of an electric motor. The stator is the part of the motor which creates the magnetic fields that turns the rotating shaft. The magnetic field is generated by electric current in the copper wires or bars slotted or wound into the stator. Our rewinder is connecting the end windings. Most people think of a motor as made up of metal. In reality, there are fiber-infused insulation paper, there are plastic wedges. The winding method even uses raffia string as temporary tensioners. In other words, many types of materials have to combine together in the hands of a real master to make a motor. It is a fascinating piece of technology. Measurement versus machining. The days of taking one measurement at a time are over. We have the means to take continuous measurements with digital sampling, not just at 1 or 2 positions, but multiple positions. We have evolved from the doctor's stethoscope to an X-ray to an MRI scan. On the left looks like an MRI scan, if you like, of a rotating shaft. It is highly exaggerated, but the shaft appears to be rotating in an S shape. The data is captured by proximity probes, like the one you see next to the graph. An off-axis rotation puts severe stress and strain on the shaft, which could weigh several tons and spin at several thousands of RPM. Again, just like in the case of the damaged motor earlier, we shift into the world of physical machining to correct the stressful behavior. Here is a picture of a horizontal machining center set up to achieve micrometer perfect roundness and concentricity of a shaft sleeve. This is achieved by aligning the sleeve to be machined with the rigid cutter and turning the sleeve against it. The size and depth of the shaft rules out common CNC machines. The CNC robotic arm simply won't have enough strength to hold the cutter steady. Condition monitoring versus constraints. My final slide in this section compares digital condition monitoring with physical constraints. In the industrial world, the most common type of failure is mechanical, and the most common precursor of mechanical failure is vibration. High vibration, or a trend of increasing vibration, usually means something is about to fail. A system of sensors placed around a machine collects vibration data, and a computer processes the data into a frequency distribution. The algorithm is based on Fourier transforms done in seconds by computer what would take hours to do by hand. The idea here is that different frequency patterns will indicate different mechanical causes of vibration. In this case, the pattern indicates a misalignment between two shafts. The diagram is obviously exaggerated because you won't need digital sensors if you can actually see misalignment with your bare eyes. But the red-hot coupling in the infrared thermograph provides proof that minor misalignment that our eyes cannot see causes significant problems at the machinery level. Okay, so your digital alarm beeps and your CM app spits out this pattern and deduces that you have a misalignment problem. You call up the maintenance crew and they advise you that they will get the job done in 3 days. 3 days, you exclaim. We already know the exact problem, so how can it take so long? And then he shows you the picture on the right. He says, "Sir, can you figure a better way to rig this pump in and out of this wall of pipes?" Condition monitoring is a no-brainer and will be pervasive in 10 years, if not shorter. CM is already standard in the cars we drive today. It will make its way into plants and vessels for sure. However, to maximize the benefits from CM will require engineers who can overcome physical constraints and take action. So we have considered the workspace versus the workshop. We considered reports versus repairs, measurement versus machining, condition monitoring versus constraints. It should be clear that we now have to deal with two worlds. We have to deal with the digital world because the speed and level of detail in that world prepares us to execute things better, faster, and timelier in the real world. But we also have to deal with the real world because it is not possible to digitize everything and live in the clouds. The human race could become extinct except to leave a copy of ourselves in a thumb drive. So what are the dangers of not recognizing this simple fact? We, or worse, our children, begin to believe that the digital world is the only world, or the better world. Closer to our industry, we risk producing screen-top engineers who do not want to get their hands dirty, who produce digital wonders, flawless reports, but who cannot do a thing in the workshop with an actual repair. What is the best attitude? Embrace both worlds and what they offer. To survive and compete in the future, you need to master two worlds. Now here's a little secret. Not everyone in the organization will have the ability to master both worlds equally well. Some will be more hands-on, while others are good at computers. Here's what we practice in SWTS. We have come to value different strengths of our workforce, and as an organization, we strive to operate successfully in the two worlds.